All right, so we're going to start up on the next virtual lecture for EAPS536, and the topic will be the monsoon, or really as a phenomenon, the monsoon, with a little bit of insight into where monsoons are found on Earth. The most common one you probably heard of is the South Asian monsoon, but there are other locations. So we'll be talking about the basic theory behind monsoons and what they are and why they exist. And so the reading is provided on the left there. There's really just one page from Hartman. Otherwise, our books do not really cover this topic very well, so we provided a couple of other introductory resources. Otherwise, we'll be working a lot with the primary literature, actually, today in this lecture. All right, so I'm going to provide some learning outcomes for today, especially because this stuff is not in our book. So we're going to be going directly to primary literature to talk about this. So I'm going to describe, well, then this is the second half of this lecture. First will be just, the goal is to be able to describe what a monsoon is and where and when they occur on Earth. Explain the theory for why monsoons suddenly start and end, and explain the theory for why land-ocean contrast contributes to its sudden onset. Okay, so we're going to begin today with just a movie about the monsoon from NASA. This is an awesome movie, and you can check it out on YouTube as well if you like.
The monsoon is a seasonal rain and wind pattern that was first described over South Asia. You see the clouds blossoming here during the summer part of the monsoon. For centuries, people have known about it, but only recently have we received enough data from satellites to really describe what's going on.
What you can see here is moist air that has evaporated from the ocean coming across India and providing rainfall driving the monsoon season. The great thing about GPM is that it allows us to see precipitating systems as a whole over land and oceans, and then as they transition from one boundary to the next.
All of this rainfall drives soil moisture over land. It's beneficial because it promotes the economic activity that people depend on, for example, agriculture. As well, it fills the rivers, which provides water for human activity and the natural environment, as well as transportation. If the rivers get too full, of course, it becomes flooding. At first, the floods you see here are fairly minor and broad scale, but then they concentrate in the few wiggly lines, which are the river basins, for example, in central eastern China.
In mountainous regions, when the ground becomes saturated due to heavy rains, it can lead to landslides. Landslides kill thousands of people every year and are primarily triggered by rainfall. They are especially common within the Himalayan region each monsoon season.
One really cool way to look at the monsoon is to do a split screen and look at the summer and the winter at the same time. In the summer, the wind is blowing onshore, bringing the moist, rain-laden air into the continent. In the wintertime, it blows off the continent.
Now, those winds are basically driven by temperature differences between the ocean and the land. And where the land is nice and warm, the air expands and it draws in the moist precipitation from the ocean waters. But in the wintertime, it's very cold, and you can see that the moisture then goes from the continent back into the oceans. Over the past 50 years or so, satellites have been used to measure precipitation all around our Earth. With that data set, we're able to understand that monsoons occur not only in South Asia and India, but in other parts of the world as well.
For example, Africa, where the temperature gradient is between the Atlantic Ocean and the Sahara Desert. The wind blows from the moist Atlantic Ocean onto West Africa, providing the moisture for the precipitation. Some of these westward moving storms provoke hurricanes over the Atlantic that occasionally make it to the U.S. Southwestern North America also has a summertime monsoon. You see high soil moisture in regions where there's a lot of precipitation in western Mexico, and later in the season this extends up into the southwestern U.S. And the southern hemisphere has a monsoon as well. This occurs in the northern hemisphere winter, which is the southern hemisphere summer, when Australia is warmer than the ocean to the north.
Having a better understanding of the global water cycle and monitoring changes over time is important for society, for our everyday lives, and our long-term future.
All right, so this is a really nice animation giving you insight using both observed data for precipitation in millimeters per day within each month. So this is averaged over some period of time in the historical record from observations each month, where you can see this north-south progression associated with the seasonality, the seasonal cycle of the Earth in general. And so superimposed on there is this really nice schematic of the Hadley circulation, where you can see it shows it right now. You're seeing it as a winter and a summer hemisphere cell, and then it becomes one dominant cell. So it's a really nice cartoon form of how the Hadley cell evolves from northern to southern hemisphere. So again, it's strongest in the cell is strongest on the winter hemisphere side. So here we're going into winter now, and you'll see the development of a strong cross-equatorial cell that goes from the northern hemisphere to the southern hemisphere. So it takes some time to look through this. But what's key is you can see here we're going February, March, April, May. There's a sudden onset, what we say, of the shift in precipitation from the near equatorial region over land from the near equatorial region over water, shifting right now over land over South Asia. So this is the South Asian monsoon you're getting to see in terms of the precipitation. And so what this animation is highlighting is that this is really a meridional or a poleward extension of the Hadley cell itself being drawn inland over land because of land-sea contrast. And so what's important for the real world is that this contributes to bringing precipitation. There's a sudden onset of enhanced precipitation over land over southern Asia. And so that is, again, it's really intimately related to the Hadley cell itself. The monsoon is not separate from the Hadley cell, but rather it's a localized region of a poleward enhancement or a poleward extension of the Hadley cell itself. Okay, so we can put this in the context of our previous lecture. We talked at the end on this work from Lindzen and Howe in 1988 of the extension of the held-Howe theory for an axisymmetric, meaning just longitude is all, there's no variation in longitude, only variation in latitude here on the x-axis, and height on the y-axis is this overturning stream function where you see it shifting, going from top to bottom of peak heating at the equator, moving it gradually off the equator to 2 degrees and to 6 degrees. So this focused on really off-equatorial heating that was very near the equator. And so what we're thinking about for the monsoon is the idea that there's going to be off-equatorial heating significantly farther away from the equator. And it's going to be associated with a subtropical continent in particular. Okay, so the first big question that we want to answer is, it's unique to the monsoon, is why does it suddenly seem to start and then suddenly end? So that's something that's unique to a monsoon. Okay, so the work that really tries to answer this question, the seminal work, is from Plum and Howe in 1992 in the Journal of Atmospheric Science, JASS. And it's a theory for how subtropical heating can cause a sudden transition to a Hadley cell overturning circulation. And so this reference is given in the bottom left. We'll include that in the Blackboard space. And I really encourage you to look at this. We're going to actually walk through this, or at least parts of this paper in detail here. And so what I'm going to do is to put up the abstract, which is nice and blurry because this is an old paper, so it's scanned in. And so we're going to you can read that all for yourself. I'm going to highlight a specific chunk of this text in this abstract, which is below a threshold forcing, the atmosphere adopts a steady state of thermal equilibrium with no meridional flow. With supercritical forcing, the state breaks down and a strong meridional circulation is predicted. The threshold forcing value is that at which the absolute vorticity of the zonal flow in gradient balance with the equilibrium temperatures, which is to say thermal wind balance, vanishes at the upper boundary. So this is actually an extension of Held-Howe and Lindzen and Howe theory that they're applying here to thinking about subtropical heating. Okay, so the setup for this problem is one of a localized maximum in heating being applied in the subtropics, so at a latitude phi naught. That's shifted shifted north of the equator, so in the northern hemisphere. So the x-axis is latitude, the y-axis is height. So you're thinking zonally symmetric. And then that heating is applied over a width of delta phi here, 15 degrees north. But they focus on 25 degrees north as their central latitude for heating that they're going to use in experiments, model simulations, as well as comparing with theory. And so I'm going to highlight that central latitude with this red dashed vertical line, as it's going to come up multiple times to help you be oriented in these plots. So that's the latitude of peak subtropical heating. Okay, so they first do an experiment with weak heating, where the peak heating, or I should say the peak potential temperature perturbation is 3 Kelvin. Again, applied at that latitude. It's shown in the red dashed line. And so the result when you do that is a very weak overturning. So let's walk through that. So in the top left is the stream function, where you can see you actually get a very weak overturning. And this overturning is actually, I'll come back to this, is driven by viscous forces. It actually doesn't need to be there at all in the absence of viscosity. And then you'll notice in the top right is the zonal wind. So you have easterly flow, equatorward of the peak heating latitude, and then westerly flow, poleward of it. And then in the bottom left is absolute angular momentum. So go back and check what that equation is if you've forgotten, but just the absolute angular momentum, when most of those contours are nearly vertical as they are on the real Earth. And then the bottom right is absolute vorticity, which is so the sum of the relative vorticity and then F, which is also nearly vertical here. So there's relatively weak perturbations, but you'll notice that the zonal wind, if you have perturbations in the zonal wind, that means you're having perturbations. You're creating relative vorticity. You're actually generating negative relative vorticity if you look in the top right. So but the key takeaway here is actually just that, in this case, the thermal equilibrium state for this weak heating profile is essentially perfectly valid. So you don't actually need to develop an overturning. You do develop a weak one in the model because there is some viscosity, as I'll come back to. But so this is a weak overturning, again, with the rising motion near the peak heating. And so what's interesting is, I'm first going to show you the kind of big result, which is that there's threshold behavior. Is that so if you vary the heating rate, so the strength of this heating at 25 degrees north, you get two regimes of behavior. So on the x-axis here is the maximum potential temperature perturbation. So we looked at 3 already before. And then the y-axis is the maximum stream function value. So it's giving you a measure of the strength of the overturning circulation. And so for weak heating, so to the left of this dashed red line is what we call subcritical forcing, meaning you're below a threshold where the radiative convective equilibrium, or the thermal equilibrium solution, is perfectly valid. Which is to say you have meridional variations in temperature associated with this heating profile, or this imposed temperature profile, and that is associated in thermal wind balance with a meridional variation in the zonal wind. And there's nothing wrong with that. There can just be perfectly happy in thermal wind balance, and there's no Hadley cell overturning that's required. And you'll notice that this dashed line extends farther out, and this is what they call the linearized solution, where you're not, which is to say you linearize the equations where you don't allow for an angular momentum conserving Hadley cell response at all. So that just extends that line out. So, but what actually happens is above this threshold is what we call supercritical forcing. So if your forcing strength is strong enough that heating or temperature maximum is large enough, the radiative convective, the thermal equilibrium solution is not allowed. We're going to go through why that is in a second. And so instead, the angular momentum conserving solution has to apply instead. And what that means, angular momentum conserving solution, going back to Held-Howe, means a Hadley cell overturning, a thermally direct overturning circulation. Just want to note, as again I'd mentioned, there's still a very weak Hadley cell, so those little, I should have said the black squares correspond to what the actual simulations produced, and the dashed lines are the theory. So you can see these two regimes. And so there is still a weak Hadley cell forming for weak heating. It's just, and this is actually driven entirely by viscous effects. So in the caption, it notes that they have a viscosity that's not zero within the model. So there is some internal mixing that helps to actually generate a weak, very weak Hadley cell overturning. Okay, so the question then is, what governs this threshold behavior? Why is there this transition between these two regimes? So we can understand that by first looking. What they present is a case now with a strong heating, so a maximum potential temperature perturbation of 12.1 Kelvin at 25 degrees north. So this is now 4 times stronger. But what they present is a linear solution only, so which is to say they take their model and they linearize the equations, and that actually inhibits the Hadley angular momentum conserving solution from forming. So it's not the Hadley cell type overturning, I should say the angular momentum conserving solution is simply not allowed. And so what's nice is this gives you basically a view of what the thermal equilibrium state looks like for this particularly strong heating. And so something really important changes. So first, what doesn't change is that, again, we have this very weak overturning as seen in the stream function. It's actually not much different than in the weaker heating case. But you'll notice there's a much stronger, so I shouldn't say it's not, it's stronger. But in this case now with this much stronger temperature perturbation, you have associated with that in thermal wind balance, because temperatures now decrease very rapidly moving north and south of 25 degrees north. That means that you have a very strong vertical wind shear, and so very strong jet stream, or I should say a very strong zonal wind. I don't want to say jet stream, zonal wind on both the north and south side of this. So again, it's easterlies to the south and westerlies to the north from angular momentum conservation. So the key thing is there's really two ways to understand this, and they're really the same thing. So first is if you look in the bottom left, the angular momentum distribution, you notice there's this little circle sticking out in the vicinity of 25 degrees north. And so that's actually a local minimum in absolute angular momentum, which means absolute angular momentum is increasing, moving north or south from phi naught. And that is a problem. That's actually impossible. So air is rising at phi naught, and so when we get into the free troposphere, we said there's the flow is essentially inviscid, which is to say there's no sources or sinks of angular momentum in the free troposphere, and so this is actually completely impossible. You cannot have a distribution of absolute angular momentum where m increases moving away from basically the source of where air is being supplied. Because if it increases, that means something has to be applying essentially a torque to increase the angular momentum as the air moves, and no such source of angular momentum exists. This is something that's formally called Hyde's theorem, and is often cited when discussing this problem. So an alternative way, which is exactly the same thing actually, is that if you look in the bottom right, the absolute vorticity distribution in that same region, you'll notice now where the zonal winds are very, very strong and negative, you actually have a region, or actually I should say, right around phi naught, you have a region of very strong anticyclonic relative vorticity. It's actually so strong that it's larger than F, and so you end up with a region where the absolute vorticity is negative. And this is actually the exact same statement as that this is impossible to sustain in a steady state. So this is would be inertially unstable. So in general, so why this is equivalent is that flow that conserves its angular momentum as it moves will have zero absolute vorticity. And so these are equivalent statements. But if you want to think about it in terms of negative absolute vorticity, it's an inertially unstable solution. So it's just not a valid steady state solution. So taken together, the point is the thermal equilibrium solution. If you just say we're going to just apply a temperature profile and then that translates to a zonal wind profile as a function of latitude and height in thermal wind balance with that temperature profile, you're going to get a state that violates the laws of physics. You actually cannot have this in a steady state. And so what that means is it's invalid, and instead a circulation has to develop. And that it will be this Hadley cell angular momentum conserving overturning circulation that must form. It absolutely must form. So you could think of this also to say that the thermal equilibrium solution, it's inertially unstable. It will generate meridional flow associated with it. It has to. Okay, so if we now go to the model and they take the same model, and now run it in the fully nonlinear mode, so not with linearized equations, that allows for an angular momentum conserving Hadley cell overturning circulation, you now get what you'd expect, which is a much, much stronger, much more robust overturning circulation, where flow is actually going across the equator near the surface towards 25 degrees north, and then it's rising and then moving back towards the southern hemisphere. So it's actually a large cross-equatorial Hadley cell overturning circulation. And so you can now see this very strong overturning, and you can actually notice the absolute vorticity contours in the lower right are highly, but they're very messy looking, which indicates how nonlinear these processes are. So the solution is valid now. Now M is now increasing monotonically with latitude, and that's because the flow has to respond to remove places where that's not true. Or you can think about it as the absolute vorticity is now positive everywhere in the northern hemisphere. So don't forget that the sign of absolute vorticity changes going into the southern hemisphere. Okay, so what defines this threshold behavior? So we actually kind of just alluded to it. We can be more specific. So this is actually the same argument as in Held-Howe theory, though we may not have made that as explicit when we went over that. What we said is that in the thermal equilibrium solution for absolute vorticity, if it ends up being less than 0 anywhere, it's not valid, and you are supercritical, and a Hadley angular momentum conserving overturning cell must form. And so they formalize this in the paper with this equation here, which I'm not going to go through, but it's just a formal equation that effectively represents this what I think is a much conceptually simpler argument about absolute vorticity, but you can go through and see it yourself. And then I've just copied some of the text on the right. So this inequality, so if the left side is less than the right side, and actually this is now, I realize, in reverse. If the left side is less than the right side, then the thermal equilibrium solution is stable and valid. And if it's not true, then this principle is violated and you have to have a Hadley cell overturning. So we predict that only the thermal equilibrium solution can exist when this equation is satisfied, and only the angular momentum conserving solution can exist when it is not. Thus 8 represents a transition from the thermal equilibrium to the Hadley cell behavior. So this gives a clear theoretical prediction for a transition between the two regimes. So just to highlight again, this is this two-regime behavior going from weaker forcing, subtropical forcing. Thermal equilibrium is fine, and then if you cross over a threshold, suddenly you have to have a Hadley cell overturning circulation. And here we're thinking again in the subtropics. So this is a poleward or subtropical extension of the Hadley cell. Okay, so we first talked about now why off-equatorial subtropical heating can generate strong overturning circulation. So why is it when we talk about the monsoon, we think about land-ocean contrast, and that's very true. So why is land-ocean contrast specifically so important for the monsoon? How does it play into to contribute to the processes that we just discussed before? So the seminal paper on this was Privé and Plum in 2007, again in the Journal of Atmospheric Sciences, which is really gives a theory for how the monsoon is drawn inland over a subtropical continent. So again, the citation's shown in the bottom left. I encourage you to check it out. I'm going to put the abstract up here again, and I'm going to highlight. You can read that on your own time. Pause it if you'd like and read through it. I'm going to highlight a couple of parts from this that we'll be talking about. So results from an aquaplanet setup, so a planet covered in water, with a localized subtropical forcing are compared with a continental case, and we're actually going to focus on the continental case part. What they find is the poleward boundary of the monsoon circulation is co-located with the maximum in subcloud, so boundary layer, moist static energy, with the monsoon rains occurring near and slightly equatorward of this maximum. So let's go through that. So as a quick reminder, what moist static energy is from the beginning of the semester, shown here per unit mass, is the sum of potential energy, sensible heat, and latent heat. And so those are the three terms, and they're nicely just added together linearly, which is really, really convenient. So again, the fourth type of energy, kinetic energy, is what we're ignoring here, hence it's static energy. as units of joules per kilogram. So what the theory really says, again, is the peak overturning in precipitation follows closely with the maximum in boundary layer moist static energy. So there's this nice schematic shown here on the left. This is actually taken from Carrie Emanuel from some past notes. And so it's shown the colors or contours of theta, so just showing kind of a stably stratified atmosphere where potential temperature increases with height. And then the solid black line shows the overturning circulation for the Hadley type overturning circulation. The dashed line shows shows a particular latitude. And you can see below all of this, there's a solid or a straight black line, and then that's the ocean, and then there's a land. And then the red line at the bottom is the profile of moist static energy versus latitude. So it starts off lower over the ocean, and then it is enhanced over land, and then decreases, though, as you go further inland to higher latitudes where it gets colder and drier. So what's special about land? Why does land matter? So land has a small capacity to retain energy. We say a small heat capacity. So what that means is when you energy input into the surface, say from solar heating, is rapidly transferred to the atmosphere. The land has small storage, and so it's transferred in the form of sensible or latent heat fluxes from the surface to the atmosphere. And so as you move towards the summer, solar heating rapidly is increasing. So what that means is surface energy fluxes from the land to the air are also rapidly increasing. And this is actually the same argument for why the diurnal cycle is much stronger over land than over ocean, why temperatures can increase so quickly during the day and decrease so quickly at night as compared to over water. So and then the second part is, why does land poleward of ocean matter? So generally, this is something we're kind of skipping over a little bit, but air tends to rise or tends to convect near a peak in boundary layer moist static energy, we'll call HB max. And this is a concept we call quasi-equilibrium, which I think will come up again in the Walker cell next lecture. But the idea is basically that the free tropospheric moist static energy is set by the boundary layer values wherever it's convecting. And so it's basically stable anywhere except when the boundary layer moist static energy can reach those values. And so the maximum in moist static energy in the boundary layer shifts inland as the surface heat flux is increased, and we're going to show what we mean by that. And so the key thing then is air flowing inland from the ocean comes in with a smaller moist static energy in the boundary layer, and so it has to travel farther inland as for surface fluxes to be able to increase HB to the value HB max, at which point then it can convect. And so this is where air doesn't quite convect at the latitude of peak moist static energy in the boundary layer, but it gets pretty close. So that's the conceptual understanding of this, of their theory. Okay, so I just want to show you, jump to two simple, more straightforward results from their experiments to demonstrate this idea. So these are Hofmahler diagrams. So the x-axis is latitude and the y-axis is time in days for 1 year, where 0 is the winter solstice. So the northern hemisphere summer is kind of in the middle of the days here, going up and down. And then the blue dashed line denotes a transition, basically a continental coastline. So there's ocean south of about 16 degrees north, and then land in quotes north of it. And they represent land by enhancing the surface heat fluxes over the land. And so keep in mind, again, solar radiation, or they apply mean sea surface temperatures that also vary, where they're stronger at lower latitudes and decrease going to higher latitudes. So the key thing is the left is, the colors denote precipitation rate. So you're seeing precipitation. Darker colors means stronger precipitation. And so the left is the case of weaker land surface heat fluxes. So there's a less of a land-ocean heat contrast, essentially. And what you notice is that during the summertime, there's a little bit of an inland, so northward propagation of precipitation, but it's pretty weak. And on the right side is a strong land surface heat flux. So the land is more land-like. There's a stronger heat flux into the atmosphere. And you'll notice something that jumps out is something that is the monsoon, which is there's this sort of relatively sudden onset of strong precipitation that shifts inland around, say, day 150 to day 200. And then there's also sort of a relatively rapid end to it. So this jump inland in the precipitation. This is really the monsoon right there. So there's this clear contrast, clear threshold behavior between weaker and stronger land surface heat fluxes. Okay, so why then is the land-ocean contrast important here? So the key thing is what's shown in the right, which is a diagram showing ocean to land at the bottom of the diagram, this transition, and then what's shown here now is the moist static energy in the thermal equilibrium state as a function of latitude, if you will, going from left to right is going poleward. And so the key thing is that the lower curve corresponds to a weaker heat flux from the surface to the atmosphere, which is to say a weaker land-ocean contrast. And you'll notice there's a peak noted in a location where the maximum in moist static energy is found. And then if you go to a stronger heat flux, this curve not only shifts upwards, so you're getting higher values of moist static energy over land, but the key is that the peak also shifts shifts poleward. And so that's what's denoted by that pink arrow. And so what this means, as they note in the figure, as the surface forcing is increased, the radiative convective equilibrium, HB, also increases over land, but not over the adjacent ocean. It increases a little bit, not much though. And so now poleward flowing air from the ocean has to go farther inland to acquire enough heat to reach that equilibrium maximum in moist static energy, and that's where then you expect convection to be able to occur. So the peak in moist static energy in the boundary layer shifts inland, and so that means air has to move farther inland essentially to be able to acquire enough energy from the surface to be able to match that and then be able to convect. So there's one more component to this, which is really important to think about, that was identified later on, actually as a part of work a couple years later, is that topography inland, overland, is also really important, has an important role for what we call insulating the monsoon region from cold, dry air. So the monsoon region is our warm, moist air coming in, we've just talked about, and you can imagine at higher latitudes, not too far poleward, you can see it in the right side of this diagram, is that air becomes much colder and much drier very quickly. So it has much lower values of boundary layer or even free tropospheric moist static energy. And so you can imagine if there were processes such as extratropical cyclones that mixed that air equatorward, it might actually act to offset some of these effects. So you can imagine, for example, if you put a mountain in, a mountain might play an important role. So we put these with these two triangles in both diagrams, however you want to think about it. The left side, the vertical axis, or up and down, is actually altitude, so makes a little bit more sense. But what you can imagine is that no matter what, any advection or any movement of air equatorward is going to try to bring in cold and dry higher latitude air with it, so lower boundary layer moist static energy. So you can see on the left side and the right side, think of it as equatorward advection of low moist static energy air. And so if you have a mountain or some physical barrier, that can actually block that from happening. And so it keeps separated the warm, moist, and the cold, dry air, hence insulated. So topography insulates the warm, moist monsoonal air, as it prevents it from mixing with the cold and dry air. If this flux were to be able to go through, this flux of low boundary layer moist static energy air would act to directly offset the enhanced surface fluxes that brings the monsoon inland. So. And so this is work done by Boos and Kwong in 2010 in Nature, which is really important work. I'm just going to highlight one the key result from their simulation. So what they did with the South Asian monsoon was to change the topography over in the Himalayas to demonstrate its importance. So I'm going to walk through these plots. So the columns on the left is upper level temperature, which actually we won't even talk about much here. The mid-level is low-level entropy, which is an analogous quantity to moist static energy. So you can think of it as theta E if you want it as well. And then the right column is precipitation in millimeters per day. So So the top row is just the regular real Earth simulation. So the you have the Himalayan plateau, the contours, the topography are shown in the black contours. And so you'll notice, there's warm, moist air being drawn well inland up into the region bounded to the north by this topography. And then you'll notice in the precipitation map that there's significant inland precipitation, particularly at the base of the orography there. So at the base of the Himalayan plateau. And then what they do is the same experiment where they remove the Himalayan plateau entirely, so there's no more topography. And what you'll notice is suddenly now the inland moist static energy, or the inland low-level entropy in the boundary layer is reduced significantly. And it's reduced so much so by mixing of cold, dry air from the polar region, or from the higher latitudes, that you actually become subcritical and you have no monsoon. So you've pushed it below that critical threshold, and so you have no more monsoon at all. And you can see that in the precipitation. There's no more inland enhancement of precipitation. And then at the bottom is a case where what they did is they actually removed the northern topography of the Himalayas, and they just kept the southern edge of it, which is sort of a wall. So to really test this idea that's purely insulation, all you need is some barrier to separate, to keep the cold and dry air from mixing with the warm and moist. Okay, let's go to Blackboard, answer a few questions about this topic.